Hey everyone, Chris here. So I thought I'd make a quick video today and just kind of show you what the new GenFEA.net analysis engine looks like and how it works. So if you want to read a bit more about it, just before we start jumping into the code, you'll find some info on the website. So BIMWERXFEA.com. You can see it over there. I'll drop it in the comments also. So right at the top under latest news, we talk a little bit about the capabilities, what it features, what it can do, and all of that. You can request early access here. So if you fill out this form, then we'll keep you updated with early beta releases, updates, and other information. If you click on documentation, it's going to take you through to the full documentation. It's reasonably well developed even at this early stage. So you'll see at a high level in the overview, it talks about what it is, what the structure at a high level looks like, how it works. Currently it's built for .NET 10, but we're working on a bridging tool for those who are still using .NET 4.8. But right now in this version I'm going to show you it's going to be .NET 10. And then there's a bit of theory here, but if you break down into it, you'll see we covered the various aspects like the model components, what that looks like, and you can read about it a bit here. We'll be expanding on this in due course, but below the class breakdowns and function breakdowns, you'll see there's a tutorials section with a whole bunch of tutorials. There's 10 of them, which covers basically everything that it currently can do. So if we just look at the linear static, you'll see this one is in metric units, and it's an end-to-end one. So it shows you the complete start-to-end example, and you can pretty much copy and paste that and run it, and then that way also learn how this works. But we'll be doing one from scratch. So what I'm going to do is we'll just create a new solution from scratch. We'll link in the libraries and you can see what that looks like, and we can talk about it a little bit. So I'll just start a new C# desktop Windows app, so Windows Forms app. We'll go next there, we'll give this a name. I'll keep it in my tutorials folder, and we'll just call this one GFA tutorial 1 for a lack of a better name. That should do it. And we're gonna make sure that we select the .NET 10 long-term support. That's what it's built on, and then we'll give that a second to open up. So let me drag this across. Right, now the first thing we want to do once the form decides to display is we want to bring in the libraries from GenFEA. So what I'll do is I'll go to dependencies. I'll click here on the browse, and you'll see there we've got the GenFEA library. So that's what you would select. Once we add that to the project, it's pretty much all we need to do. We can set this to 64-bit. The library is built to 64-bit anyway, so let's do the same here. It's not essential, but it is preferred. So we'll set that to 64-bit, and we'll quickly just run this and make sure everything works with a blank form as we expect to, and there we go. So that's all fine and well. Now, the reason I did this is because if you work through the tutorials here, it'll talk about how to apply the MKL solvers. So I think we do it here somewhere. There we go, solvers and performers. So it tells you here we need to copy the MKL Paradiso distribution libraries into a subfolder in your solution, right? You don't need it. The GenFEA engine works without those plug-in solvers with its own built-in direct sparse solvers, but it's going to be much faster and much better, so I do recommend it. So what I would do is once I've built my 64-bit debug version, what I do is I right-click there on the solution name, and we go to Open in File Explorer, and we go into bin, we go into the 64-bit, we go into debug, and you'll see if we go into the build folder, it's under the framework, so there it is, and here we can see our solution files. Now the stuff you want to copy across, I've already got it here. It'll be in a folder called runtimes, so I'll just place this here in the root of where my exe sits, and if we go into runtimes, you'll see it's got some subfolders, and then it's got a bunch of DLLs there. These DLLs are the ones that come from the Intel 1 MKL API. So if we have a look at what that looks like on my machine, yours might be slightly different. But under my C drive, under program files, 32-bit, if we go into Intel, we go into one API, we go to MKL, and we go to 2025.2, and we go into bin finally. That's where all the MKL libraries sit. We don't need all of these, of course. There's quite a lot of them, they're quite big. Just the ones that we've got in here. We'll place a download link for this entire runtimes folder as a resource on the website at some point, so it'll be easy to access. It's just so that you are aware that that is what it needs to look like in order to access those libraries. Okay, that's good enough. Now we can start. What I'll do is I'll drag a button here onto my form. We don't have to be too specific here. We'll just call this one test. You can provide better names if you want, and we'll just do a static linear test. So I'll just write static linear there, and that's going to be what we'll be testing. So there's a couple of things to make life easier. There's a bunch of imports. Now I've already pasted them, copied them onto another part on my computer, and then I just paste them in here. It makes life a bit easier. Obviously, if you don't do that, you can do that while you're coding, or just type out the full namespace and classes if you really want, but this just makes it a bit easier. So the way this works, and this is explained in the documentation, the developer documentation in detail, but the way this works is we'll start off by creating a model. So the model definition is the first part. So what we'll do is we'll set up a new model, and we'll just say that this is a new FE model. You'll see the autocomplete there picking that up, and then we can pass a unit system into this. So we'll create we'll create a model here using metric units. We support, you can see here actually. So there's your standard metric one. We support imperial units and then other metric unit configurations that you can enter there. And it's as simple as that. That's how you set up a new model. Now, we've got this model placeholder now, and what we want to do is we want to start adding information to it. So the logical thing to do would be to start with a material. So this is actually, this autocomplete here is not completely wrong, but what I prefer to do is to just assign a material ID first. So we'll go here and we'll say that we're going to create a material for steel, and we'll just do that and assign a value of 1 to it. Right. Now that that's done, we can go and we can add this to our model with some properties. So we'll go model.add material, and again we'll see what is required here. We need to create a new material derivative. So we'll say we're going to create a iso linear elastic material, the base class being material. And if we just look at what this looks like, what we're expecting, we need an ID, a name for the material, the modulus, the Poisson ratio, and if we want to optionally, we can add the density, and that can be used to compute the own weight automatically, which I'll talk about in a bit. So the ID we want to specify here is that material ID, what did I call it again? Steel mat ID, sorry, there we go. So steel mat ID, we're going to call this one steel. We'll make that value there for the modulus of elasticity to that one, and we can see the autocomplete actually does a good job. So we've got a Poisson ratio there, and we've got the density 7,850 kilograms per cubic meter. So that's it. We've just added a new material just like that. Now we're going to do the same for sections. Next we'll add some sections, right? So I'll just paste this in here so you don't have to watch me type all of this out. A bit of a type mismatch there, doesn't matter. So you can see when we add the section, in this case we use the simple cross section. There's different section types. You can create fiber section as well. We just created a simple cross section here. It's got the properties here that we've set up. So we've got an ID, we give it a name, it's got a material associated with it. So there's the material we created and added to the model, and we assign that now to the section. And then we've got our various properties that we enter here for the section. So of course, at any point you can look at the properties here, and that'll give you an indicator of which are required and which ones of those are optional. So obviously the ones with the question mark there are optional parameters that we can set, and you'll see there's values for A, Z, and C, W. Those will be ones that you would need to apply if you wanted to use the 7th degree of freedom, the warping torsion, which we're not going to do right now. I'll do that in a follow-up session. Anyway, so now that that's done, let's create our nodes. We're just going to do a simple beam with 2 nodes. Again, I'll copy and paste that in there and talk through it. So creating our first node, we want a reference to that because we're going to use it again later to assign that to the beam that we'll create to define the start and end position. You can see it's pretty simple. So we create a node, we've got an ID, and it's got a vector 3D, which is a XYZ coordinate. So in this one, you can see we're working in meters. So we've got X, Y, and Z there. So that means that we're drawing a beam along the global Y axis at a length of 5 meters. That's it. Now for setting up supports, this is quite simple also. So now that we've got reference to those nodes, we can actually access the set support property. And what we want to do is to create a new support definition, a new node support definition, and we can add here multiple constraints. So in this one, we're going to fix all for translations in both of them. But then on the first node, we're also going to fix for rotation about Y. So if we wanted to add more here, we can go ahead and add another setting here. So whatever it is that you want to fix. All right. So that's how simple it is to define supports. There are some other properties that you can use here as well. You'll see if I go to my node, we can directly access the support as well. So we can either use the set support, but we can also go to the support property, and if we look here, you can see we can fix the support here. We can check if it's fixed, we can do some prescribed displacement, we can release it if we want. Right, now that that's done, what we want to do is actually add those nodes 1 and 2 to the model. So model add node, and it's going to be the actual reference that we've set up here for that node. So now we've got a model with materials. Well, a material, a section definition, nodes, and supports assigned with those nodes. Now the next bit is creating our beam entity with those 2 nodes. So again, I'm pasting code in here just to make it a little bit faster, but we can talk through it. Just fixing a typo there. Anyway, so we create a beam ID. It doesn't have to start at 1 or 0. It can be any arbitrary number as long as they're sequential and make sense, or unique at the very least. In this one, I've added releases. I'll talk about that later. We'll just comment it out for now so it doesn't become confusing. But here we go again. So we've got the model, and we're adding a new beam member. So in GenFEAx analysis engine, we've got a parent class, which is like a container, which is the beam member. And then automatically in GenFEA, we split the beam elements by a number of segments. And I'm going to jump into the elements here, and I'll show you what I mean. So you can see there's a beam member, and this one is the high-level 3D member. But within the beam member, we have got beam 3D segments, and this is the element, the discretized elements that sits within the beam member. So how that works is we create a new beam member. There we go. You can see we are assigning properties to it, but notice we've got a segments property there. So we can set this to any number. And you can assign that differently to every beam element, and that just means that it's going to split up or discretize that element by equal segments, meaning you don't have to create central nodes manually in order to extract values from the mid of the beam, for example, displacements or moments or whatever. And you can create as many segments as you want. It'll automatically do that. So that's pretty neat. So here we've got at the top, we've got the ID, we've got the start and the end nodes, so that's node I and node J. And then we've got the section ID, and we've got the material ID assigned to it. The segments is 4, and then you can choose your theory. So we can use a Timoshenko theory, or we can use the Euler-Bernoulli hypothesis. So we'll select Timoshenko for now, so that includes shear deformation. All right. Including warping torsion, I've set to false here because we won't include that now. I'll talk about that a bit later. And then you can see the orientation. We can set up some specific beam orientations here. So you can see here we've got beam orientation. Currently it's set to null. If we wanted to add a specific beam orientation there, you'll see that we've got a class with various properties and methods in here. And then once we've set it up, we can rotate elements around their longitudinal axis along the length of the beam, which is its local x, which we're not going to do now. And the same for releases. So with the releases, again, you can set up your reference to beam end releases. And in here we can have multiple properties. Currently we have got a release for the rotation about z at the start node, and we set that is true. And what we can do is we can add to this. So we can go here again, we can say, sorry, that should be, come on. So here we can now go and we can see we've got I, j, nodes, and we've got x, y, and z, and we can continue adding to that to create our end release conditions, and we can plug that into the releases if we want, right? So that's how we add the beam member. Now, the next thing we want to do is to start adding some loads. So I'm going to just provide, again, a random ID there, 100. We create a new load case. All you need to enter is the ID and the name of the load case. Now, defining loads is quite simple. What I've done here earlier and part of my testing stuff was just to calculate the own weight based on the density and the volume there. So that's the value you see here. But what we've got here is a beam uniform load. Of course, you can have point loads. You can have a beam point load at a distance, and so on and so forth. There's various loading elements. If you want to have a look at them, I recommend you go and look here at the loads components. So you can see we've got beam point load, beam uniform load, the load container element, load cases, load combinations, and then nodal loads and self-weight settings and shell area loads, and so on and so forth. So we'll use the beam uniform load. It's got an ID. That's not the load case. Later we'll add the load to the load case. Actually, we're going to do it soon. So you'll see we've got the load case there. Sorry, we're already doing it. We've got the load case there. We're adding the load to it, which is a new beam uniform load. It's got an ID. There is the member that it's associated with. And then we've got here the load per length. So whatever your units are that you're going to be using. And we want to use here a negative 154.778 newtons per meter. And you can see that's our load per length that we've got here, and it's a vector, so we specify the magnitude for x, y, and z directions. And then we've got two options here for the axis. It can either be global or we can make this local. So we'll stick with global, but just so you know that those are your options. Right, so now we've got our load applied there. Now, I did mention that we can add the own weight automatically, and I just want to show you what that looks like. So within the self-weight case, if we type that out, so you'll see under loads, we've got a self-weight property, and in here we can do a bunch of stuff. So we can say include shell elements, is it enabled, true or false, include line elements, the gravity magnitude, the factor, and that's pretty much it. And we can set those values. By default, I'll create a breakpoint here so you can see what happens when I run this. But by default, it'll use 9.82 as the value for the gravity magnitude, which is what it should be. All right, so now that we've got that defined, now we're going to add the load case twice, the own weight twice, because we've already done it here manually as a linear load, and here I'm adding the self weight again. So keep that in mind. I'll switch this to false, and later I'll switch it to true so you can see it doubling up. All right, so what we do now is in the model, we add the load case. We've now created the load case. We've assigned a load to it, mapped it to an element, set the magnitude, and then what we do is we add the entire load case to the model. Now you can also create load combinations. So we can say LCMB1 equals new load combination. Now load combinations would take a name and a string. So just to show you an example, let's just make this one 101, and we'll just say LCMB1, all right, as the name. Now if we look at the properties we've got here, you'll see we can now add a load case ID and we can add a factor, right? So that means we've got a load combination container that we can set up, and we can set the factors, assign the loads to it, and that'll automatically then contain an element called terms here, which is going to be the list of load cases and factors of the combinations that we want to set up. I'm not going to do it for this exercise, but it's there. I'm just showing you so you're aware of it. Good. So now we've got a complete model here pretty much. We've got the model, we've got the material, the model container, we've got the material, we've got the section, we've got nodes, we've got supports, we've got the beam member with its properties, we've got the load case, we've got the load assigned to it, and we've added that to the model. So the next bit is setting up the analysis. First, we create our in-memory result store. So GenFEAx can export, it's got some IO functions. It can export to CSV, and you can import at the moment ufm.in files. This is just for validation, so it helps us for testing, but it'll remain part of the library in any case in future. But the results are stored in memory, so we create a new in-memory result store, and then what we'll do is we're going to set up the MKL party, so backend, and I'll show you what that works. So I'm going to say here that this is optional for MKL. All right. Now, what this is going to do is it's going to create a new solver entity, and then there's various types. So in the documentation, you can look at the various backends M types. We're going to select 2. The next part we want to do is to set up the actual options. So I've created a new variable here. It's sparse factorization options, and you can see here we've set the thread count. We've got reuse, symbolic factorization, and we've got apply, fill, reducing, ordering. That's all just stuff to speed up the sparse matrix computation. So there is a way to set the thread count to the maximum here. I just don't know, can't remember where to do that. I don't want to keep you watching me, but I set it manually here. You can set it to the maximum thread counts on your computer to pick it up automatically on the system. I'm sure if I quickly Google it, I'll find it, but anyway, you can find it too. And then finally, we want to set up the solver. So what we've done is we've got a result store. We've set up a backend using the MKL party. So we've got the options set for the sparse factorization options. Now we're creating the solver, and into the sparse direct solver adapter, we're going to plug in the back end. So this is the MKL Paradiso, and we're going to plug in the options for our direct sparse solver. Now that that is done, the next bit is to set up the analysis. We create an analysis container, and we're going to say it's a new linear static analysis, and you'll see if we just do a test here, so var analysis xx, and let's go here, new linear analysis. So there's linear buckling, linear dynamic, blah blah blah. So all of the solvers available, because we've done the using statements here at the top, so they all would sit under there. All right, analyses. So we've got that set up. That's pretty good. So we've got the backend in there, we've got the options there, and so under the analysis we want to plug in the solver. So it's a linear static analysis. We plug in the solver. The solver again was referencing the backend and the options that we've got in there. Now I'm going to just move this out of this little block here, because I want to show you that we can switch on and switch off the MKL backend solver. Right, and then we're going to run the analysis using the input model and the result store, right? So that's how that all ties together. And once it's done, we want to extract some information from the result store. So to do that, we're going to set up a step key, because we can do time history analysis and staging analysis with GenFEAx. We need to set up a step. This is linear static, so the step is going to be 0, but we need to create a step key in any case, right? So when we create a new step key, we specify the analysis case kind. So you can see we've got load cases an option here. We've got staging, buckling, response spectrum, etc. So there's various types of outputs. What we're looking for is just a simple load case. We've got a case ID. We've got a stage ID. By default, it's going to be only the first stage. There's only one. Because we don't have construction staging in this model. That's something I'll do in a future video. We are specifying the first index, the step index, which is 0, and obviously the time here is 0 as well, because it's a linear static analysis. Right, and that's going to be the step information. So each step will have its own set of properties within the model once the analysis has been run. But we are not referring to the analysis output here. We are just saying this is our step definition. So if we wanted to start extracting information from the model, the way we do it is we go to the results, which is set up here as our in-memory results store. From there, we've got various methods and functions. So in here, we've got try, get, beam, result. We pass in the step, so there you can see where the step comes into play. We say which elements, so the beam ID, we're going to pass in there. And then we want an output variable where it's going to save this as, and this in this case, it's automatically going to do the type conversion. So you can see it's going to be a beam result that we get out of here. And if we do the same for nodes, it's going to be a node result output. And just to show you, if we go to results, what we can do here is we can add shell Gauss point results. We can get all the beam results as a collection. We can get all buckling mode infos, all the node results, shell results, get all the steps in one list, set beam results, snapshot information. We can store information, we can try to retrieve information, and so on and so forth. So there's a whole bunch of stuff you can do there. It's pretty extensive. Now we can stop here and we can start extracting results, but this is going to be, remember I said that the beam is split into segments, so when we get the information, it's still going to be the various stations. This value here, the BR, which is going to be a beam result, is going to be in various stations. So if we look at the BR properties, you'll see it's got stations. It'll have things like moments here, so you can see we've got end warping I and end warping J, because they won't be internal. We've got the end by moments for I and J and end reaction moments for I and J. So that is in the overall member, but the internal elements is going to sit within the beam station. So what we'll do is we'll create a new beam station result at the mid, and you'll see that this one actually wouldn't be mid because it's sitting at station 0, which is the first one. In this one there'll be 4 stations, right? So what we'll do is we'll just copy this across, so you can see now we're gonna run this little for each loop, and what we'll do is we'll try to get the center. So I know it's gonna be halfway through, so we just find the mid and we say whichever station is, there'll be 5 stations because there's 4 segments, apologies. So there'll be a start and end and then 3 internal nodes, so 5 stations, 4 segments, right? So we want the one in the middle. So we've got mid here and we're going to find mid and we'll assign it when it's close to 2.5 meters from the start. So that's how we find the mid station. Now I'm going to do the same for the start station, except I don't have to search for it. I know it's going to be the first one, right? So it's going to be 0 in that list. And that's pretty much all we need to do. So the rest I'm going to paste in here from here on is just the reporting. So I'm creating an empty string and then we're looking at support reactions. So earlier here we said results, try get node results step. We defined the step key up here. We're going to say that it's for node 1 and the out variable is R1. So if we look at R1 here, we can see here we're calling it and we can find the reaction force. This is all 3 directions. So if we go reaction moment or reaction force, we can then look at X, Y, and Z if we want to. And you can see there's a bunch of other properties. But what we'll do is we'll just extract X, Y, and Z. And then here is that mid station that we've extracted, the beam result station. And this is going to give us the distance from I, from the start. We expect to see 2.5 meters there. Then we're looking at the shear and the moment. So the shear we're taking at the start, so that's the station 0. The moment in the mid we're taking from the mid one that we've set up here. And then of course it's got its sub properties. So if we just look at what those are is, so we've got our, let's go down here alphabetically. So we've got deflection, we've got moments, and we've got forces, and we've got rotations there. So the forces would be NX, so that's axial, and then we've got our shear here, and this will be rotation. And then we've got the warping output here as well, which in this case, for this example, is going to be null, empty, or 0. Okay, and there's the deflection. We do the same for. That's pretty much it. So now we've set it up, and we should be able to run this. Now, I'll put a breakpoint here later, but for now, let's just run this and see what happens. So it runs, compiles, we click on that, and we can see we get our output that we've just set up. Great. So minus 0.45 millimeters deflection there. We can see the moment, we can see the shear, we can see the distance, and we can see the reactions there for node 1 and node 2. So that's X, Y, and Z. Right, that's great. Now let's just quickly put a breakpoint here because we switched the self-weight off. And I want to show you the properties here. So if we run through and we just look at the self-weight here, so you'll see here, by default it'll be disabled even if I didn't switch it off here, but the default is disabled. So you can switch it on. The default factor is always 1. The gravity there, as I said, is minus 9.80665, direction, etc., etc. So that's what that looks like. Now let's just go ahead and switch on the own weight. So we had 0.45-ish there for displacement in the mid. If we run this again, we expect to see double, so 0.91, which is exactly what we expect to see because we've now doubled up on the self-weight, right? So quite easy. Now we've got the MKL set up here. I want to show you if I just wanted to disable the MKL. We've set up the back end and the options and we've passed that into the linear static analysis. If I remove that optional iLinear solver here from the constructor for this base class and we run it again, essentially what that means is it runs exactly the same analysis. We get the same results, but it's using the built-in sparse direct solver. So it's not using the options here, it's not using the backend, it's not multi-threaded, and it's not as fast as the MKL. You can pretty much not see the difference here, but when you start working with larger models with a lot more elements, then there's an obvious difference. It's exponential depending on the size of the matrix. So yeah, definitely cool to be able to have that option for a MKL solver. It makes it crazy fast compared to the original C++ code from other tools that we've tested with, like UFM, for example. It's on par, so it runs extremely quick, and the results check out. So yeah, we'll make the downloads for this available soon. It's almost ready. It's in the final stages. It can pretty much do everything it needs to do. We're just doing some validations and a little bit of cleaning up and documentation. It's not very well documented. You'll see if we create new cross-section, it doesn't have any descriptors here, so we're working on that and adding a bit more content around it. Some of them do. You can see here it's telling you it converts user-facing values to and from internal metric to imperial units and blah blah blah. So you can see it is there, but we need to do a bit more. A lot of them are just without any supporting context. So just hang in there with us. But it's pretty exciting. I think you'd agree if this is the kind of thing that you like to do, and if you've played around with analysis engines before. It's fully object orientated, and we've tried to make it intuitive and flexible as possible. There's a lot more to it. I'd recommend you have a look at the documentation because it's going to give you a good idea of everything it can do, and definitely look at the examples here that we've got. So here is a time history analysis example, what it does, how it works. We've got a modal analysis here, how that plugs in, how the eigen solvers work. We've got a response spectrum, buckling, p delta, all of those, even staging analysis. So yeah, exciting. What we're going to do next is we'll set up a GPT that's fine-tuned on this data, and some additional samples and tutorials, and we'll make that publicly available. So that'll be an AI agent or GPT that'll be able to help you develop your GenFEAx code, and all you need to do is to know where to plug it into and how to run it, essentially. So if you're interested, have a look at the comments and register your interest in the GenFEAx engine. Thanks for watching and have a great day. Bye.